So we've done a lot of work with velocity and time graphs. We're now going to just transfer that knowledge so that we can take a velocity time graph and turn it into a displacement time or an acceleration time, and vice versa. So here's a displacement time graph, and the main thing we need to know is just sort of what the different shapes of lines will show us. So we can see here, if we've got a steep gradient, then that means a fast and steady speed. However, if it's a curved line going upwards, that means that it's accelerating. Okay, so this curve, if it was a constant acceleration, would show as a straight line on a velocity time, but only if it was constant acceleration. This line here, however, you can see that it's a steady speed, so there's no change in that velocity, so on a velocity time graph it will come up as 0. Then with the red line we've got a steady speed. Okay, obviously a horizontal line, we can see there's no change in displacement, so that is stationary. It's got a velocity of 0, so on a velocity time graph it would just show us a constant horizontal line at 0. And then finally, displacement is going backwards here, so the velocity would be negative. Okay, now we've got the same example using a velocity time graph. So we've got a slow acceleration here, a faster acceleration, steady speed, so it's holding at whatever speed that is there that it reads off at. Slowing down. Okay, so it's got a negative velocity. It doesn't necessarily mean it's going backwards. Okay, and we can see that it's not going backwards because it's still got a positive acceleration. If, however, it dropped below a line, it would then be going backwards as it does here. Okay, so this is a backward section because its velocity is below 0. Here we've got it being stopped, and here we've got a steady speed going backwards. Now what we want to be able to achieve is to translate the information from a velocity time graph up here onto an acceleration time graph. And you can see I've just put in dotted lines to match up the times where important things are happening. So in my first section here I've got a constant acceleration, but it's quite a small acceleration. So for that whole time period it's going to be a small constant acceleration. Okay, so it's staying at that same acceleration level the whole time, and it's only just above 0, it's quite small. Then we look at the steeper part. Okay, again it's constant because it's a straight line, but this time it's a greater acceleration. So that's going to be somewhere up here. Of course, if we actually had numerical values on our graph, we could work out the exact gradient by looking at the figures, and that would give us the values on the acceleration, but this is just a sketch for now. Okay, now we've got a steady speed, so there's no change in acceleration. So here I'm at the 0 line. Okay, no change in acceleration at all. Here then we've got a negative acceleration, and it's very steep. So it's going to be negative and it's going to be large. Okay. Next section we've got it's stopped, and so there's no change in acceleration, so we're back at 0 again. Now we've got a negative gradient, so negative acceleration, but not as much as it was before. And then here we've got a constant velocity, so there's no change in acceleration. So once again, we're back at the 0 acceleration line. So you'll see from this that an acceleration time graph quite often has got these distinct sections as it changes. So here's an exam question going the other way. They've given us an acceleration time graph, and we've got to plot the velocity time graph from it. Okay, I've chosen only positive velocity, as because it's talking about a race, we're obviously not expecting the runner to be going backwards. So we're also told that he begins this stretch at a final speed of 4. Okay, so I'm going to put 4 on my graph. And I know that's where my first point is going to be from. Also the key times that I want are 4, 10 and 16. Okay. So looking at what's happening here, I've got a 0.8 meters per second squared acceleration for those first 4 seconds. So it's going to be a shape like this on my graph, I just don't know what figure it's going up to yet. So I'll draw the shape on, and then I need to be able to just read off what that time is. So I'm thinking about what I've got. In this section is all constant acceleration, so I'm actually able to use suvat for that section. So I might do that over here. So displacement, I don't know anything about. Initial velocity, it tells me is 4. Final velocity is what I want to figure out. Acceleration, I'm told, is 0.8, and my time is 4. Okay, So from that information I can use v equals u plus at. So my final velocity is going to be 4 plus 0.8 times 4, and that's going to come out to be 7.2. Okay, so this number just up here is 7.2. Okay, then for the next section we've got an acceleration of 0, so that means that the velocity is not changing. Okay, so it's not changed, it's stayed constant at that height there. Then for my final section, I've got a negative acceleration, which suggests that it's going to be slowing down. So here I've got minus 0.2. So again I can do the same formula that I did for the first part, v equals u plus at, and my second velocity is going to be my 7.2 plus, and then my acceleration now is minus 0.2 times by the time, which is 6. Okay, from 10 to 16 is 6 seconds. So I've got 7.2 minus 1.2, which is 6 meters per second. So I'm going down to 6, which is going to be round about this level, like so. Try and draw that a bit straighter. Okay, so that's our rough sketch. Of course you're going to make sure that you do it with a ruler, and you always emphasise your dotted lines wherever there's anything which is important. Okay, part B just says calculate the distance over which he sprints. So that's now using our velocity time graph and working out the area underneath it. So for part B, the area is going to be made up of this trapezium here. Okay, so it's going to be section 1, section 2, and section 3. Okay, so section 1, as I've got limited space, I'm just going to talk through this. So it's the area of a trapezium, so it's going to be a half 4 times 4 plus 7.2, and then times by the width, which is 4, coming out to be 22.4. My next section is a square, which is 7.2 tall, sorry, a rectangle, 7.2 tall and 6 wide, coming in at 43.2. And the third section is another trapezium, with its parallel sides being 7.2 and 6, and its width being 6. And that comes out as 39.6. So altogether, we've got 105.2 metres that he sprints over. So he's starting just before the 100-metre line of the last bit of the race. We've talked about this mistake a lot, but just to check, we've got a velocity time graph here, and the question says, what is the total distance travelled in this journey? This person has said, well, they want the distance, they started at 0, they finished at 80, and the time was 60. Remember that you can't do that, that the Suvat equations only apply when there's a constant acceleration. So you could do Suvat for this section, and then for that section, and then for this one, but you can't do it for the whole lot all in one go. In order to answer this question properly, we'd need to split this up into shape 1, shape 2, and shape 3. Or of course you could also do this all in one go as a trapezium if you'd prefer, then add your distances together. And this is a higher order thinking question for this topic. You recognise the graph from the earlier example, but this time they haven't given you the initial starting velocity. They've only said that this is over the final 100 metres. So you know that the distance travelled in this is 100 metres in total. So you can sketch out the shape of your velocity time graph and then think about the fact that you know the relationship between each of the velocities, you just don't know what it starts at. So try putting an x in for your starting value, work out the area underneath involving that x and setting it equal to 0, and see if then you can find out the initial velocity that it would have had to start the journey at.